Okay, there is one request. Please do not bring your coffee cups inside the auditorium. Thank you. I was not saying that.
Is this on? Okay, so we'll get started. So thanks to the organizers for inviting me to give this talk. So I'm going to talk to you about measuring the polarization of hadronic W bosons at the LHC. And this is work done with my PhD students, Songchap Takde and Will Shepard, who is at Sam Houston State. So you'll see that the first version of this paper was uploaded to the archive just after the pandemic started. But we have significantly updated our results, and we hope to put out a second version of the paper soon. Okay, so let me start with some very basic idea for the motivation for why we want to measure W boson polarization. And I'll try to convince you that's actually, in fact, one of the most important measurements that the LHC will actually make. The second thing I'll do is talk about how we'll measure the polarization using polarized Ws, first at the parton level to try to understand how you'd infer the polarization of the W if you knew everything about its parton level decays. And then in a detector, obviously what we see is different from the partons, but I'll show you how we constructed a proxy variable P Theta, which allows us to infer something about the parton level distribution, and therefore allows us to reconstruct the polarization of the W boson. I will construct templates of this proxy variable, and then longitudinal W bosons will have a different template. Transverse W bosons will have a different template for this distribution, and that's what will allow us to separate the different polarization states of W bosons. And finally, I'll talk about how we construct some pseudo-experiments to show the effectiveness of this tool to measure the polarization of W bosons and some results. Okay, so let's start with some motivation. Okay, so in the standard model, if you one of the main reasons the LHC was built was on a no-lose theorem, because if you have longitudinal W boson scattering without the Higgs boson, and remember this was before 2012, we did not know for sure if the Higgs boson exists or not, but we already know that longitudinal W scattering by itself is a problem. Massive vector bosons, their amplitude for their scattering grows with energy as energy square, so energy square over MW square. So at some energy, you run into problems with tree-level unitarity, okay, and your predictions break down for what the probability amplitude is. So in the standard model, this problem is resolved by the exchange of a Higgs boson, where this amplitude for this diagram also grows as the energy square, but it appears with a negative sign. More importantly, the coupling of this 4-point W boson vertex is exactly the same as these couplings, G, which show up in the Higgs coupling to W bosons. This is a very key feature because it allows for an exact cancellation between this bad high energy growth of these amplitudes, and therefore restores unitarity of the standard model. So the standard model is a unitary theory, okay, but we do not know whether the Higgs boson that we have seen at the experiment in 2012 is really the standard model of, is the Higgs boson of the standard model. As we heard yesterday, the degree of compositeness of this Higgs boson is measured to worse precision than that of a pion. So it's possible that these couplings, right now they're allowed to deviate by 10% from the standard model. Even a little bit of deviation would restore your problem of unitarity violation in these scattering amplitudes. So it's really important to measure this Higgs coupling to W's very precisely. So now, given that the Higgs coupling we don't know for sure how close this Higgs boson coupling is to the standard model prediction, you could imagine that it's scaled by some value A away from the standard model prediction, A is equal to 1 being the standard model value. So with this scaling, again, you would get an imperfect cancellation between these two amplitudes, and the scattering amplitude would again grow with energy. So you would like to measure, again, you would like to restore unitarity in some way. The theory should be unitary. It's one of those sacred principles that seems almost tautological. And one of the ways this can be done, if the Higgs boson is only partially responsible for unitarity restoration, is you could have something like a Techni-Rho exchange. This is in fact what analogous to in QCD, pion scattering is unitarized mainly by vector meson resonances. And so you could have a vector resonance coming in at some high energy scale, possibly even inaccessible at the LHC. Okay, and but this could restore unitarity. But the way you detect the signatures of this is you would see this anomalous growth at high energies of WW scattering. In particular, anomalous growth of longitudinal W scattering, because the longitudinal modes are the ones that eat the Goldstone bosons. Okay, so it's really important to measure WW scattering at high energies. And in particular, you want to measure longitudinal W scattering at high energies, which is why it's important to measure the polarizations of W bosons. So let's talk about how you actually measure WW scattering at the LHC. So at the LHC, you're actually colliding protons and not W bosons, but these protons can radiate W bosons, and these W bosons can scatter with each other to go into another two W bosons. And along with this, you get two forward jets plus the decay products of these Ws. So this is a cross-section of the detector to show you what you would actually see in your experiment. You see two forward jets, those being these two jets, and you also see the decay products of these Ws. Since you're looking at high energy WW scattering, because of relativistic beaming, the decay products of this W tend to be collimated along this cone, and the decay products of the other W are collimated along this cone. Now, the current measurement of WW scattering is done typically using the semi-leptonic channel. Okay, if you want to measure the polarization in VBS. The advantage of this technique is that, of course, you have relatively lower background because you're looking for a lepton plus missing energy and some jets. And one of the advantages is the missing neutrino kinematics is reconstructible up to a twofold ambiguity. So you fully know if this, let's say this W decays to lepton and neutrino, you can measure its polarization by looking at the angular distribution of its decay products. Even though you do not see the neutrino, you can reconstruct its momentum, and therefore you can reconstruct the polarization of the leptonically decaying W boson. Okay. The disadvantage of this is that the second W boson it has a polarization which you don't know. Okay, so you cannot measure the spin correlation between these two Ws. And since you're particularly interested in longitudinal W boson scattering, you cannot really test the unitarity of the scattering, okay, just by measuring the polarization of this W plus alone. So you really need to measure both the W boson polarizations. Okay. So a possible solution could be to look at the WW in the fully leptonic channel where both decay leptonically. The problem with this is that you have too much missing energy. You have two missing neutrinos, and that does not allow you to reconstruct the decay products of this W or this W, and therefore you cannot reconstruct the polarizations. Or at least it becomes very, very difficult. Okay? So the alternative solution is to use the semi-leptonic channel where one decays to a lepton and neutrino, but you now make an ambitious attempt to measure the polarization of a W which is decaying to hadrons. Okay, and the advantage of this is that you have a higher branching fraction to hadrons compared to leptons. Okay, 70% of the time a W boson will decay to hadrons. Both decay products are seen because you decay to quarks, and those quarks radiate, give you the shower. And you can see those decay products, at least in principle, you can use them to reconstruct the W polarization. So now what you can do is in semi-leptonic measurements, you can use the hadronic final states from this W. If you could, in principle, measure this polarization, you could get the spin correlation between these two Ws, and you can test for unitarity of longitudinal W scattering. Okay. The challenge with this kind of measurement is there are hadronic backgrounds to this, because your signal you're looking for is a lepton, neutrino, jet, and some jets from this W, maybe one or two. So it's lepton, missing ET, and jets, which has a large QCD background, okay, from let's say W plus jets. Yeah, that's the purpose of this talk, okay, is to explain how you will determine the polarization of a hadronic W. Okay. Okay, so the Parton-level W decay, okay, let me explain what you will do in principle at Parton level, and then I'll talk about what you will do for the hadronically decaying W boson. So if you have a W boson, and let's imagine that it's moving along this direction, this is its boost axis in the lab frame, but now we're going to its rest frame. So in its rest frame, let's say it decays to quarks, so it decays to an up quark and a down bar quark, and the angle that the up quark makes is, let's say, theta star. Okay, this is in the rest frame of the W plus. Now, you can use simple angular momentum conservation arguments to argue that the amplitude for decay of this W boson into quarks at this particular angle theta star depends on the polarization of this W plus. So if the W plus is polarized right-handedly, the amplitude goes as 1 minus cosine theta star by 2. If the W plus is polarized left-handedly, it goes as 1 plus cosine theta star by 2. If it's longitudinally polarized, it goes as sine theta by root 2. What does this mean? It means that if your W plus is polarized this way, then you have a strong preference for cosine theta is equal to 0, is equal to minus 1, which would correspond to the up and down quarks being emitted along the boost axis. Okay, so that would be true if the W is transversely polarized. The preference is for the up and down quarks to be emitted along the boost axis. If the W plus is longitudinally polarized, there's a preference for the up and down bar quarks to be emitted perpendicular to the boost axis. Okay, so in principle, if you had access to this theta star, that is the angle in the rest frame of the W boson decay, you could infer the polarization of the W boson statistically. Okay, so now in principle, again, of course, now one of the things we know at hadron level is this will give rise to a jet, this will give rise to a jet, and those jets do not typically come with a charge. So you're not able to distinguish between which jet corresponds to the up quark and which corresponds to the down quark. So you cannot really tell the difference between theta star and pi minus theta star, or equivalently, you can't tell the difference between cosine theta star and minus cosine theta star. So what you can measure, at least in principle, would be d sigma by d mod cosine theta star. Okay, so what that means is you can't really distinguish between the plus minus polarizations, but you can tell the difference between transverse and longitudinal polarization. You can tell the difference between something where the quarks are preferentially emitted this way versus the quarks preferentially emitted this way. So you have some distribution of what, or some prediction of what you expect. So transversely polarized W bosons would have a distribution which goes as 1 plus mod cosine theta square. Longitudinally polarized W bosons would have a distribution which goes as 1 minus cosine theta square. So this is 1 minus cosine theta square. It's normalized by a factor of 3 by 2. And this is 1 plus cosine theta square normalized by 3 by 4. 0 being, 0 corresponds to emission this way, theta is 90 degrees, okay? Where, so there's a preference for longitudinal Ws to emit at 90 degrees, whereas for transverse Ws, there's a stronger preference to emit along the axis, the boost axis. So now, if you had access experimentally to the distribution of a statistical sample of W bosons decaying at various angles theta star, all you have to do is fit that distribution. So imagine this is the distribution that you get, and you knew this distribution, you would fit it to a linear combination of these templates, okay, of what you expect for transverse W bosons, what you expect for longitudinal W bosons, and you would extract out the transverse polarization fraction and the longitudinal polarization fraction as fit parameters, okay? So you can extract out those fit parameters and say that 80% of the W in this sample, 80% are transversely polarized, 20% are longitudinally polarized, okay? Okay, so now what changes when you go to the hadron level? Okay, so the hadron level is much more complicated, okay, because you're not just looking at single quarks anymore. So a single quark in a detector actually first gives you a shower, okay, and so it radiates at the parton level. These partons combine into hadrons, and these hadrons eventually deposit their energy inside your calorimeter. So you get something called a jet. Okay, so and roughly speaking, this jet momentum should correspond to the momentum of that initial quark or gluon that initiated the jet. So now for a W boson which is decaying, you decay to 2 quarks, but depending on the boost of the W boson, the more boosted the W boson is, this jet which is coming out from each quark gets more and more collimated, okay, as you go to higher and higher boosts. So eventually, this spray of particles kind of merge together into a single spray, which you collect as a single jet at the LHC. Okay, so what you need to do is now you need to apply some kind of tagging algorithm to distinguish between this kind of boosted jet, which can arise from a W boson decay, and the jet initiated by single quarks or gluons, which come from QCD. Okay, so you want to separate out these two things, and within these kind of jets, you want to identify the polarization of these W bosons, okay, by learning something about the rest frame angular distribution of these quarks. Okay, so for those of you not familiar with jets, let me give you a quick primer on how jet, various algorithms that are applied at the LHC for jets. So there's this, the first step is to do what is called jet clustering, which is you collect all of these, the spray of particles in your detector, and you have an algorithm to combine them and decide which ones are close enough to be classified as a jet. Okay. So since we're looking at these W bosons, you get what are called fat jets. So you need to use a large jet radius to cluster them. Okay, so we use something called a Cambridge-Arkin algorithm with an R is equal to 1.0 to cluster these jets. The second thing that needs to be done is something called jet grooming. So besides radiation or these hadrons which come from the quark or gluon that you're interested in, you will also have soft radiation, which gives rise to softer energy deposits, but those are coming from your underlying event or pileup. And you want to remove those. So you want to remove these kind of soft and wide angle energy deposits. And these jet grooming algorithms allow you to remove this kind of soft stuff. What this does is it allows a better reconstruction of the jet mass. So now these two algorithms are applied to every single jet that you have in your experimental measurement. But in addition to this, you do something called jet tagging, which allows you to distinguish between these fat jets which come from W bosons and the kind of jets that you get from regular QCD. So the first jet tagging algorithm that you can apply is something called mass tagging, which is you simply demand that the jet mass, since it's initiated by a W boson, this fat jet should have a mass which is roughly that of the W boson. Okay, so you apply some kind of cut, let's say between 60 and 100 GeV of this jet mass, and you see a distribution here. This has a lot of QCD background, but you see a little excess here, and that excess is from fat jets which are initiated by a W boson. Okay, so in principle, this is one thing that you can do for jet tagging, but this is still not good enough. So you can still remove a lot more background of QCD by applying something called n-subjettiness tagging. So this is a typical jet, a cluster of energy deposits in the eta phi plane, so in pseudo-rapidity and azimuth. What you can do is you can apply this algorithm for n-subjettiness tagging to identify whether this jet looks like it has two clusters or one cluster. Okay, so you see that this one is actually initiated by a W, and it seems to have two clusters, which you can see are pretty well separated from each other. This is a jet initiated by QCD, and it has more or less a single cluster, but the algorithm attempts to find two different clusters. Okay, and it quantifies how well it can find two clusters by a variable called this n-subjettiness ratio, tau2 by tau1, which is how two subjeti it is versus how one subjeti it is. And this number here is 0.29. This number here is 0.73. The lower the number, the more preference it is for having two distinct clusters in it. Okay, so this object looks more two subjeti. If you set some threshold cut, like let's say 0.3, then things which are below that cut, you call them W jets. Things which are above that cut, you call them QCD jets. Of course, some small amount of QCD jets will still pass as W bosons, and they will be some kind of background, okay, that you must account for. So when trying to measure the polarization, you will not only have longitudinal Ws and transverse Ws, you will also have this mix of background QCD, which you need to separate out. Okay. Okay, so now if we look at W boson polarization in the lab frame, okay, so if I boost my Parton-level kinematics to the lab, so now this up and down quark, okay, after a large boost, the up quark will, if the angle is acute, the up quark will have a larger momentum, whereas the down bar quark would have a slightly smaller momentum and be at a slightly wider angle. Okay, so now if I want to measure, remember I want to reconstruct this theta star, and that would tell me the polarization of this W boson, okay, statistically. So how do I reconstruct the polarization of this W boson from these final state quarks? And remember, these final state quarks are what are effectively giving rise to these subjets, okay? So one way you can do this, and this is what CMS has tried to do, is to use the opening angle between these quarks, or at the hadron level, the opening angle between these subjets, okay? The opening angle between these subjets is related to sine theta star, okay? So you can directly, from the measurement of this opening angle, you can try to get the value of theta star. However, this is not a very good variable to use because, for example, if you look at how theta opening behaves as a function of cosine theta star, it looks like this. It looks very flat, okay, for a large range of cosine theta star, and it looks even flatter as I go to large boosts. Okay, so this is going up in energy of the W boson. So if I'm interested in measuring high energy W bosons and I try to measure the opening angle, you can see that if I make a small error in the measurement of the opening angle, I will make a large error in my inference of cosine theta star. So the traditional technique which has been used by the experiments is not a very good variable to use because you would make large errors on trying to reconstruct theta star, and therefore large errors on trying to reconstruct the polarization of the W boson. So instead, what we have done in our work is we proposed an alternative variable, and this variable doesn't suffer from the same problem. So it turns out that besides using the opening angle between these two subjects, you can also use, it turns out that there's this exact relationship, cosine theta star, is the difference in energies between these up and down bar quarks divided by the momentum of the W jet. So you can just see intuitively why this makes sense. Okay, so if you, for example, look at longitudinal Ws, where the quarks are emitted this way, theta star is 90 degrees, cosine theta star is 0. But in that case, when I boost them, since they're both perpendicular to the boost axis, they would end up having equal energy in the lab frame, okay, and then the right-hand side would also be 0. So, so this works. And in the other case, when the W is transverse, so let's say the up is emitted here, the down bar is emitted here, theta is 0, cosine theta is 1, then the up carries all the energy, okay, and the down bar carries none of the energy when I boost to the lab frame, okay. So, so delta E would just be the energy by momentum, and since this is assumed to be massless, this would be 1. Okay, so this is an exact relationship, which, so the claim is now that as a proxy variable, instead of trying to learn theta star from a measurement of the opening angle, you can use the energy difference between these subjects to learn about theta star, that rest frame opening angle, which is sensitive to the W boson polarization. Yeah. Yeah, I will talk about this. I will talk about that next. Okay, so you'll just see it in a slide or two. Okay, so what we do at the hadron level is we look at these jets. Okay, you look at the ones that pass your tagging cuts. And now that you have these subjects, this n subjectness algorithm returns those subjects for you. You take the energy difference between your subjects, divide by the momentum of this jet. That ratio is this proxy variable P theta, which is what we define. And this is a proxy for cosine theta star. Okay, at the hadron level, this is allowing you to infer exactly what cosine theta star should be. So one of these is a U bar, a U, and one of this is D. You don't know which is which. That's why you're measuring mod cosine theta star, not cosine theta star itself. Yeah. Yeah. So mod is important, right? You can't. So you cannot tell the difference between a positively and a negatively polarized W boson because of this, but you can only tell transverse versus longitudinal. Yeah. Okay, so now we construct templates of what this P theta distribution would look like. I'll skip over most of this, but we construct a theoretical simulation sample of PP to WW via scalar. This ends up giving you longitudinal Ws, or via pseudo-scalar resonance, and this gives you transverse Ws. We simulate at Parton level and MADGraph, and then we do showering and hydronization in Pythia. We don't really do a detector simulation at all, but we have some estimate of what the errors are due to detector effects. Okay, and then what we do is we take our W jets, which are boosted, and we reconstruct this P theta variable and construct its distribution. So in principle, P theta should reconstruct to cosine theta star, or if I plot its distribution, it should look like 1 plus cosine theta cosine square theta for longitudinal Ws, 1 minus cosine square theta for transverse Ws. Now, coming to the point that Tuhin raised, okay, the grooming algorithm actually biases you. So there are two distortions that you get in the distribution. One is your tagging efficiency is different depending on what cosine theta star is. The larger cosine theta star is, that means that the larger one of the emitted particles, the U or the D bar, is very soft and very wide angle, which means that that it will fail the tagging cuts because your grooming algorithm, okay, removes a very, so imagine one of this was a very low energy deposit, which is far away. Your grooming algorithm removes it, okay, and therefore it fails the tagging cut. So it would no longer pass the tagging cuts. And so you'd see that at large cosine theta star, you basically have very poor efficiency for selecting those kind of Ws. So there's an inherent bias in like picking out objects with large cosine theta stars. In addition, your soft drop algorithm modulates, okay, your selection as of W bosons as a function of cosine theta star. Okay, so this is the 1 plus cosine theta square distribution. Yeah. Yes. Yes, I agree. Yes, that is true. But we have checked across different grooming algorithms. Okay, and now we have not simulated detector noise yet, but I'll give you some estimate and explain to you. Okay. So this is the 1 plus cosine theta square distribution, the idealized distribution. But because of your bias in your selection, okay, this would get modulated to something like this red curve over here. This is similarly for transverse W's. This is the ideal 1 minus cosine square theta distribution. But again, because of the bias of your selection effect, okay, you get a distribution that looks like this. Now, in addition to this, you could say that I'm not really measuring cosine theta star, I'm measuring the proxy variable P theta, and you could look at the extra distortion that that would cause. But what we find is P theta is, so this is from Monte Carlo truth, P theta excellently reconstructs cosine theta star, at least till cosine theta star is 0.8. Okay, so almost always P theta is gives you a very faithful reconstruction of this cosine theta star. Okay, so the only distortion really in the distribution away from 1 plus cosine square theta is the selection effect of grooming algorithm plus your tagging cuts. Okay. Okay, so finally what we get is we get these templates. Okay, so we get this template for longitudinal W bosons, this template for transverse W bosons, and we also simulated what you get for background QCD. Okay, and you get this kind of template. So in principle, I could do now a fit to all these three kind of distributions. Okay, and try to extract what fraction of the jets that I'm seeing are longitudinal Ws versus transverse Ws versus background. Yeah. Yeah, so I'll just say something about this. So I'm going to show you the discriminatory power. But before that, actually what we did was, this is where we apply a fixed cut on n sub jettiness. So instead of applying a cut on n sub jettiness, we only apply a mass tagging cut. And rather we look at the 2D distribution of this proxy variable P theta and this tau2 variable. Okay, and when you look at both of these together, then you see a big difference between longitudinal Ws, transverse Ws, and tau2 and background. Because if I just applied a cut here to reject background, okay, then the distributions for, let's say, longitudinal, transverse, and the background, they do not look all that different. But if I look at the 2D correlations, I really see that there's very big differences. So instead of using 1D templates, we actually end up using these 2D templates, okay, to discriminate. So, quickly applying this to the main purpose, which is vector boson scattering at the LHC, we just do a quick estimate, okay, of the number of events that we expect to see at the 13 TeV LHC with 3,000 inverse femtobarns of data. So I took the current CMS study, which is at 138 inverse femtobarns, and scaled it up. So the QCD background events roughly you'd expect with 3,000 inverse femtobarns is about 32,000, out of which you'll have 2,000 hadronic boosted W events. Sorry, this would be your signal, this would be your background. So, and let's say you have 20% longitudinal W. So you would have 400% longitudinal, 1,600 transverse. So now what we can do is we generate pseudo data by taking a linear combination of the longitudinal, transverse, and background templates in this ratio, 400, 1,600, 32,000, and we get the sum. We add Poissonian noise, okay, and that gives us this distribution. So this is what we consider pseudo data. Now we take our pseudo data and now we try to decompose the pseudo data into those templates, into linear combinations of these templates by doing a fit, okay? And so we try to reconstruct these numbers, 400, 1,600, and 32,000, and this is what we get, okay? 480 plus minus 140, 1,671 plus minus 140, and so on. So rather than looking at absolute numbers, let's look at the polarization fraction. The true polarization fraction of longitudinal Ws is, true fraction of longitudinal Ws is 1.8%, and true fraction of transverse Ws is 4.7%. The rest is all background, right? Your background dominated. When we reconstruct in the pseudo experiment, we reconstruct fairly well within 1 sigma, okay, and the error is also pretty small. So the polarization fraction can be extracted at about the 10 to 30% level in these hadronic decays at the high luminosity LHC, okay? We repeated this for many pseudo experiments to check that this makes sense. So these results are using P theta and tau2 alone, and it can be further improved with a multivariate analysis fitting for the kinematic distributions. So let me conclude by saying that the measurement of W polarization in hadronic channels is extremely important for understanding the unitarity of vector boson scattering. So besides measuring the Higgs couplings, unitarity of vector boson scattering is probably one of the most important things that the LHC will measure. Okay, and what we have done is we've constructed a new proxy variable which is sensitive to the polarization of these boosted hadronic Ws, which will allow you to test this unitarity of longitudinal W scattering. It uses jet substructure techniques to measure the energy difference of the subjets, which is much more reliable as a way to reconstruct cosine theta star than the opening angle currently used by CMS. And we expect to be able to reconstruct the polarization fractions of W bosons to within something like 10 to 30% at the high luminosity LHC with 3 Atterbarn inversive data. And this tool is, of course, I gave you one application, which is WW scattering, but there are many other applications for this tool. You could use it for new resonance searches decaying to WW. If I want to know whether it's a scalar or a pseudo-scalar resonance, I could use it to measure polarizations of tops in top decay. Okay, thank you.
Okay. Thank you. Questions, comments?
Thanks. Just one naive question, actually 2 questions. The first one, you wanted to look at WL to WL. Fine, you have reconstructed or differentiated between WLs and WTs in the final state. Now, initial state Ws, do you know whether, how do you know whether they're WTs or WLs?
Yeah, so strictly speaking, you cannot measure that. Though what you have to do is you look at the polarization combinations, the spin correlation of all final states. So you look at all final state combinations, longitudinal, transverse, 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 longitudinal, longitudinal. And that fraction is sensitive to all the different combinations of transverse, transverse scattering to transverse, transverse, longitudinal, 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 and so on.
Mm-hmm.
So you don't fully test exactly longitudinal, longitudinal, but you test more combinations of different possibilities.
And is that information going to be enough for looking at this perturbative unitarity?
Of perturbative unitarity?
I mean, that's what one of your goals is, right? To look at the unitarity.
Well, you'll more strongly constrain it, let's say, than if you did not use this measurement.
Okay, fine. I have to think a little more about that. My second question, have you thought of, or is it feasible even to look at WW to TT bar?
And measure the polarization in the final?
Well, maybe not measure polarization, even just to look, identify WW to TT bar, because that too is going to show a loss of unitarity, maybe not as strongly as WW to WW, but it will still show, if you have a change in the Higgs couplings or change, you introduce a techni rho.
My naive guess would be you'd be heavily background dominated by QCD production of TT bar.
Right.
So
it would be, but if you go in for the boosted guys, would that be of any use? Because you also want boosted
again,
stuff here.
electroweak production, I think, would be far subdominant even at high energies. Right? TT bar is just strongly.
Yes.
If you use VBF kinematics cuts, I mean, otherwise you wouldn't do any VBF measurement if you were going to be down, down.
No, but VBF is, there's no strong production channel, right? There's
glue into Higgs is a strong production, right? I mean, it's not a electron.
I mean, that's very weak coupling, right? So
no, but I mean, what I'm really trying to say is that kinematic region is so spectacular that it may need not be hopeless. Exactly. No, it doesn't, because if the glues do that,
the beam is connected to 2 jets and TT bar in the middle, no? With a glue coming in.
Yeah, but the point that I'm making is that when it is a W, you don't have a hadronic activity, no? That's what I mean by the
we are looking for TT bar plus jets.
No, but the point I'm making is that there is no hadronic connection between when it is a, perhaps that is not correct, because when it is a top, I will have additional emissions in the rapidity space.
Okay, so, sorry, let's go to the next question. Gagan.
So very naive question. The fact you have 2 forward jet, and as you know that in the high luminosity phase, we'll have high granularity calorimeter. And so the thing is, how would it help, for your background suppression and indirectly affecting your sensitivity of this, the cos theta star modulus, whatever you were saying. So how much that will help? If
you're asking about how, so if I understand your question, you're asking how does identification of these two forward jets help
Yeah,
you suppress the
yeah,
background?
exactly.
Yeah, so typically what you demand, so let me again show that picture of, the detector. So what you demand is that you have these two forward jets, okay, which have a large pseudo-rapidity separation. They are high PT jets, okay, and they have a large, high PT in the sense maybe greater than 30 GeV or whatever cut you set, and they have a large invariant mass, okay. All of these together are very hard to replicate. I mean, you still have a lot of background QCD, but you can suppress a lot of it. Yeah, so let me in fact show you the CMS result, okay, which I have on one slide, right? So this is the current measurement of VBF. So this is the current measurement of VBF. This is based on the invariant mass of those two forward jets. And you see this is the background, okay, which is dominated by W plus jets. And it falls off as I go to high invariant mass. But if I look at the signal for W boson scattering, that doesn't fall off as fast, okay, as this falls off. So the higher the cut, the more you can suppress this background.
Okay, Dipankar.
Sorry, I'm confused here. So this is for when you say there's no hadronic activity in between the jets. Have one W is actually hadronic. So this would
No, this is W plus jets, right? So it's semi-leptonic.
Semi-leptonic. Okay.
Yeah.
Both semi-leptonic.
No, semi-leptonic means one is decaying to leptons.
What I meant by that, but you still have hadronic activity in between the forward jets, no?
You will have some, yes.
That is not going to pass you.
That's not going to pass?
Apple versus orange, no?
I don't understand. What
so
exactly?
one of the W is hadronic.
Yes, one is hadronic.
So you have the veto is not working, no?
I'm not, what am I trying to veto? I'm trying to veto background, right? I'm trying to veto W plus jets.
Activity in between two forward jets.
Yes.
So, but I'm confused. Am I missing something? But my signal doesn't pass that cut, no?
No, I'm not, okay, it's large invariant mass for these two jets. Other hadronic activity
that is by definition because they are back to back or large rapidity.
That's
so all events will have large invariant mass between them.
No, but you see it has this distribution, right? So this is the distribution for WW scattering. This is the distribution for background, right? For background, that will not be the case, right? For background, the jets will be produced at all angles. So the likelihood that you have a large invariant mass is smaller at high invariant mass.
Dipankar.
Yeah, the signal is quite small. Like even here, right? You have 2000 hadronic boosted Ws compared to 32,000 background, right? So within this, we're claiming that you can still measure the polarization fraction.
Oh, one question you showed about this composition of QCD jets, your W transverse and longitudinal.
Yeah.
Now in between will come the detector noise.
Yes.
And, how well you think you have done that? I mean,
yeah, so I have one backup slide to show on this. We haven't done the study carefully, but I can tell you what we have, okay? So this is the error on that proxy variable P theta. And the error would come from how well you can measure the energies of the subjects, because P theta is constructed by an energy difference between the subjects. So that error would be some order 1 factor times the error resolution of the subjects, okay? This error resolution, there's no published error resolution for subjects, but if you use the jet energy resolution, that is about 10%, okay? So, so which means that P theta, roughly speaking, so I don't know whether there's I'm not claiming that this is what you will get for subjects. I'm saying if you assume this is what you get for subjects, then this can be measured to within 0.1, and that is roughly the binning that we used on P theta when doing the fits. Okay, because you'll make that much will be a smearing on P theta.
Okay, there's another question.
Sorry, one small question. Maybe taking cues from the previous question. So when you talked about this WW scattering, instead of actually like motivating it as a mean to probe the WWH coupling, since we already somehow, and to some degree, we know the WWH coupling from Higgs data, right, from signal strengths. So we can use that as an input and then instead try to verify that WW quartic coupling instead, whether that is actually G square. So would this scattering be, can it be motivated to actually check the SU2 nature of the W boson? Like instead of, since you already know WWH from an independent source, can you try to motivate it just to probe that quartic coupling, direct quartic coupling? And
Yeah, that's a good question. So people try to do this with triple gauge boson couplings because so WW scattering will also have triple gauge boson coupling.
Yes, yes. That.
So now you're asking, can you actually measure the quartic in?
Yeah, so it would be a independent cross check of the quartic coupling, and if the quartic coupling turns out to be the pure SU2 gauge coupling, then you are sure about the pure SU2 nature of the double boson, because you know the WWH coupling from an independent source now. So can you basically turn the?
Yeah, I suppose you could do a global fit to WW scattering and Higgs couplings to check this. Yes, because the Higgs coupling to W's has error also, right?
Yeah, yeah.
You need to do a global fit to both.
All right. Okay.
One question is that, do you have plan to implement it in a sort of a data-driven way, in a sense that without relying on simulation for your templates, did you think of having it?
So we had a couple of ideas that the referees were not happy with, okay, to use W plus jets and things like that. But the backgrounds basically are the issue, whether you'll get a pure sample of longitudinal Ws in your detector. Is there anything that gives you pure samples of longitudinal Ws or transverse Ws? And it's not very clear that you can do that from purely data-driven way. Because you'll still have QCD contamination even in those samples. The transverse? Mm-hmm. Yeah. Yeah.
Okay, I don't see any other hands raised. So let us thank the speaker. And the next speaker is Rusa Mandal, and she will
Okay, so no, I can see. So thank you very much for the organizers for the invitation. And I am asked to talk about new physics and mainly related to the flavor anomalies. So far we know that the standard model is too good for us, and basically we pretend that we understand almost everything within it, and we are desperately looking for some signatures of BSM particles. And so far we didn't see any direct signature, and we know there are some reasons why we need to go beyond the standard model physics. So basically the indirect evidence of dark matter and matter-antimatter asymmetry. So this has somehow, one can say somehow it has to deal with some kind of cosmological implementation of the standard model of particle physics. And then we have already have some kind of experimental evidences, like we have seen the tiny neutrino masses, which were predicted to be massless. And also we have seen kind of very high mass hierarchy between all the fermion masses, what we have actually observed. So these two things, either we can actually extend the standard model and incorporate the neutrino masses, and also for the fermion mass hierarchy, we can see like some kind of ad hoc fine tuning is embedded in the standard model parameters. And then we already heard a nice talk by Jian yesterday and also today. So we know the problem of electroweak mass hierarchy. So basically the Higgs mass is unstable under quantum correction, and we somehow think that the new dynamics should show up at the level of TeV range. Basically from these four reasons, indirect or say even direct, we do not see any any definite energy scale where we should actually expect the BSM physics, except for this one, the last one. And so far, so the well-motivated popular BSM constructions like supersymmetry, those are some sort of becoming less and less appealing due to the null results from experiments. So in that sense, we can think that we should look for new directions. So whenever I say new directions, it has nothing to do with the new paradigm what we actually learned from the talk by Jian. So here what I mostly talk about, say, suppose we concentrate on fermion mass hierarchy and somehow try to relate whatever the hints we have from the low energy data from the so-called flavor anomalies. So just for the younger audience, so what I mean by the fermion mass hierarchy, so basically when we look at the mass scale of the electron and the top, so there is kind of 7 orders of magnitude difference. And when we look at from the Lagrangian point of view, so we see the gauge couplings are same for all the fermions. So there is a flavor degeneracy, and we have a much larger group, which is called the flavor symmetry. And this is again broken by the Higgs-Yukawa interaction. And what we end up getting is like this uses, for example, this is the up-type Yukawa matrix, and then we look at the elements here. So the top quark entry is roughly 1, and all other elements are somehow very small. So this is known to be the old flavor puzzle, like why these masses and the mixings of these standard model fermions, whether there is some kind of reasoning behind this, or all these are like just some accidental thing which is appearing here. So the aim is just somehow to connect this old flavor puzzle with the new flavor puzzles, or say the B anomalies, and we have also heard about these things yesterday and also today. So we have this anomaly which is seen in the flavor changing neutral current B2SLL. The ratio of the muon and electron channel is very well predicted within the accuracy of 1% in the standard model. And starting from like say 2014, LHCb has performed several measurements, and they are consistently seeing some depletion in the prediction compared to the standard model prediction. And these deviations are at the level of 2 sigma. So there is also another channel which is B sub s to phi mu mu. So if we look at the quark level transition, this is again the B2SLL channel. But in this case, this observable is not a cleaner one like the ratios, but this is kind of the differential branching fraction. And you can see even for the muon channel in the same Q square range, which is like 1 to 6 GeV square, we see a kind of depletion in the data compared to the prediction. And this is at the level of 3 sigma. Then I move to the another one, which is called RD star. We have also heard yesterday in Soumitra's talk. So again, some kind of deviation when we construct the ratios. So these are semi-electronic channels. So whenever we are constructing the ratios, the hadronic uncertainties cancel a lot. And recently LHCb has published their result, which is close to the Bubber measurement. And this red blob is the current world average, which is deviating from the standard model, which is this black error bar at the level of 3 sigma. So in this case, you can see the experimental value is higher than the standard model prediction. And similar thing is also observed, say another ratio, which is the same quark level transition B to C tau nu, but in terms of like different mesons in the final state. And in this case, although the uncertainty is quite large from LHCb, but the trend is same, like the data is larger than the standard model prediction at the level. It's less than 2 sigma. And another interesting puzzle, what we have this muon magnetic moment. So what we see, like the main source of uncertainty is coming into this G-2 measurement is from this hadronic vacuum polarization. And Fermilab has confirmed the BNL data. And if we just compare the data with the hadronic vacuum polarization estimates from the data-driven approach, then we see kind of 4 sigma deviation. But of course, there are predictions from lattice collaborations, and also they do not agree among themselves. So, I mean, in principle, we can wait for them to come in an agreement. And even if we say like there is something wrong going on in the data-driven approach, then we also try to somehow alter the electroweak precision data in some sense. So for this talk, I am not going to scrutinize whether these are actually real, the so-called real anomalies, whether there is some kind of experimental flaw or from the theoretical, there is some part is missing. So my talk is mostly based on like, if we are really seeing some hints, then what can we actually infer from for the new physics? So then how do we proceed? All these are like low energy processes. So for example, the best tool we have is the EFT. So if we just say like at dimension 6 level, so if we consider the 4 fermion operators, which are constructed from the standard model fields and the symmetry, which are known as the SMEFT, so then we get like 59 operators. Now, if we actually break them into their flavor parts, so then we end up getting like 2,500 operators. So the point is, if we try to identify the non-zero effects in this whole space, so it's kind of hopeless situation to find anything non-zero with this full set. So the idea is like what we always try to use the symmetry assumption. Either we select a subset based on some symmetry on the UV theory, or we somehow treat the anomalies or say whatever the hints we are seeing independently. So why I say treat them independently? Because if we just look at the energy scale which can involve in this EFT operators. So for example, as I mentioned, RK star, those are loop level process in the standard model. So if we just consider this 4 fermion operator and we make no assumption on the Wilson coefficient, so the roughly to explain the deviation, we need the new physics scale to be around 30 TeV. However, for the RD star, which is a tree level process, so in this case, to explain the anomaly, the scale can be as low as 3 TeV. Now it comes like whether this assumption on the Wilson coefficient is kind of robust. Of course not. You can have different structures depending upon the flavor structure of the new physics. So for example, if we assume minimal flavor violation, that means the flavor violation is only arising from the standard model fields and new physics operators, they are not involved in this. They do not generate any new source of flavor violation. Then you can see roughly to explain B2SLL anomaly, you can even go to the 6 TeV range because the Wilson coefficient will vary as like the standard model scale, standard model flavor violation. One can also generate the MFV in the new physics context via another loop. So you get another extra loop factor and you can further lower the scale. So in principle, whatever the new physics scale we are expecting from these hints, they actually depend a lot on how we are dealing with the flavor dynamics. Some similar kind of argument can also be made for say G-2 if we just consider the SMEFT leading operator, which is shown here. So without any assumption on this, you can even push the new physics scale to say 100 TeV. And of course, you can lower the scale if you have some kind of new physics model with say chiral enhancement. So that I'm not going into the details. So then since we need to probe the flavor structure of the new physics or say BSM particles, so one of the main ways is to go with the simplified models. That means at least one new physics particle is present at a time, or say, yeah. So you can say some various possibilities, say for B2S, the prime extra-dimensional leptoquarks, and in this case, 2 HDMs, W prime and leptoquarks. So leptoquarks appear both the places. And these are nothing but some, say, scalar or vector particle, which can turn a lepton into a quark. And it was like tabulated long back. It's not a new idea. It's there from 70s. And it's just revived by, one can say, because of this peculiar nature of the B anomalies. So then again, the question is, suppose we consider this leptoquark scenario. So then how do we determine this Yukawa structure? So the leptoquark coupling with the lepton and the quarks. So one way is just to roughly fit the data. So we have kind of then large number of free parameters in the theory. Another again is we physicists love to use the symmetries. So you assume some kind of underlying symmetry in the UV model, which will not only reduce the parameter, also will give some kind of theoretical motivation to deal with such cases. So as I already mentioned, the minimal flavor violation, which is actually not, you cannot explain the current nature of B anomalies only with this context. So our aim was to extend with the leptoquark scenarios. So what we did, whatever the Yukawa matrices we have for the leptoquark couplings, we made them as flavor spurions. So that means they are kind of auxiliary fields, and they have kind of all the standard model fermions. They have Fogart-Nelson charges, which are like some U1 distinguishable U1 charges for all these standard model fermions. So just to give an idea of how this will work. So let's take a SMEF operators, 4 fermion operators with standard model quark doublet and lepton doublet. So in a generic EFT, all these C Wilson coefficients are order 1 numbers. So we have kind of 81 parameters. Then if we impose minimal flavor violation only in the quark sector, we're not introducing anything in the lepton sector. So reduce the number of parameters to 6 from here, like 3 complex numbers. So how this Fogart-Nelson charges actually work? So basically, in that case, this Wilson coefficient will go as a in the power of some small U1 breaking term lambda, and all these are the generation dependent charges. But in this case, we again end up getting this large number of parameters. So what we did, if we just embed leptoquarks into this Fogart-Nelson scenario, then we can actually divide it into 2 parts, and all these S, they are called these leptoquark spurions, and we have kind of a reasonable number of parameters in context of this 4 fermion operator. So then the standard model flavor structure, we already know the CKM we need to produce, because you remember we have introduced charges for all standard model fermions. So that gives some constants, and also we can then fix the charges for the left-handed quarks up to say a common offset D. And then the left and right combination are also fixed by the Yukawa, the standard model quark and the lepton masses. But the charge lepton mixing is of course unknown, so we have a kind of freedom to choose the lepton charges. And what we did, we just took up, yes. In this case, you can see like, so when we embed the leptoquarks into this spurion business, so then we can actually generate the standard model fermion masses, the flavor structure, and we can, I mean, all these couplings are actually fixed by the charges and the masses. I mean, by the CKM and the masses. So these are not at all free parameters like normal Yukawa couplings for the leptoquarks. So all these are like some fixed quantities which we need because we already have seen these quarks and leptons. So maybe I'll just give you an example. So here you see like these are Yukawa couplings, these S tildes. So in a normal leptoquark case, these are 3x3 matrices. But in this case, what I can show you, okay, in the next. So as I mentioned, so in this case, since the left-handed charges for the quarks are fixed and also some sort in the leptons, and we take into account the constants from all other possible channels, we end up getting only for the 2 solutions for all these spurions, leptoquark spurions. So these are not at all any free parameter which one can fit the data to get the anomalies or say remain in the constraints. So yes, so then what I was mentioning, so basically we want to explain these channels and then we have constraints from all other possible channels because we cannot just turn off one coupling and say this is 0 because we don't need it. Because in this case, it's all related to the standard model flavor structure. And that's why we end up getting only 2 solutions for the charges are possible for say all these 3 leptoquark spurions. And with this, so basically we can actually explain the anomalies. So you see in the whole model where there are 3 new Ikawa couplings, which are 3 cross 3 matrices. So in principle, 27 parameters, we have only 3 parameters in our whole setup because of the flavor structure we embedded there. And so the question is, okay, the discrepancies are reduced, we can explain the anomalies, but what are the other signatures we are seeing? So here are some decay modes where the standard model branching fractions are given in some cases which are 0 and even very small. And the third column is the experimental upper limit. So in some cases you can see we have kind of huge enhancement compared to the standard model one, and it's just 1 order less, 1 order below than the current experimental sensitivity. So it's very kind of easy to say confirm and falsify these kind of scenarios. And this is also kind of normal situation when we try to explain this neutral current and both charge current anomalies, because these are kind of some channels of B decays which relate muon and tau. So just a side remark. So this leptoquark can also contribute to the muon G-2, which I was showing you earlier. So it's a kind of a loop which is dominated by a top quark. And in this case, we end up getting like we are having kind of strong suppression because of this tau to mu gamma rate. And in principle, whatever the solution we have, that only the 2 choices we have, it's not possible to explain the deviation from the Fermilab data and the data-driven approach, whatever we are seeing now. So in principle, if we had the freedom to choose all the leptoquark couplings independently, it is possible to do, but in this scenario, it is not. So this was just one example to deal with, say, this charge current and neutral current anomalies. So I will just quickly say another interesting channel, which is also a flavor changing neutral current. But in this case, instead of the leptons, charged leptons, we have, say, neutrinos in the final state. So experimentally, it is much more challenging because of the 2 missing neutrinos, and no signal has been observed in this mode. However, very recently, and we also heard yesterday in Diego's talk, that Bell has come up with a very innovative tagging technique. So in this case, they are using some inclusive tagging technique. So basically, they are not reconstructing the full the B tag site. So they are using some kind of decay topologies to actually balance both the sides of tagging and the signal side. And in this case, they are expecting some kind of signal. Even in this case, they have the result of very preliminary data. So if we just roughly take this into account, and I hope Bill will very soon will have some kind of update on this channel. So at the moment, it goes kind of like 2 times than the standard model prediction with a very large error. So just in another work, we actually tried to see whether this kind of enhancement is possible in terms of some, say, simplified model which can explain these other charge current and neutral current anomalies which I was talking in the first part of my talk. So here you see, so basically this S1 and R2, these are different like scalar leptoquarks and vector leptoquarks. This is also Z prime. So in some cases, you can see it's possible to obtain a 2 times enhancement for this B2K new bar channel, or say B2K star new bar channel, if we are really seeing any hint in this anomalous, in this flavor changing neutral current decays. And similarly, for the combined explanation, we find like S3 and the U3 is kind of some it can show some desired enhancement in these 2 channels. So of course, measurement for this mode will be very crucial to falsify this BSM setup. So this was just from this hints which we are seeing in the semi-leptonic channel. And just I would like to mention another some kind of puzzle which is also seen in a non-leptonic mode. So this is a decay mode where B decays to a d sub s or with a pion. So you don't see any leptons in the final state. And these are kind of, there are two more channels in this set. So these are color allowed 3 channels. And you see like different quark flavors in the final state. So there is no possibility of having annihilation diagram or even penguin diagrams. So in that sense, these are, although always these hadronic modes are difficult to deal with, but in that sense, these modes are somehow easier, I would say, compared to the other ones where we deal with annihilation and penguin diagrams. So what is interesting is like currently the theory predictions, which actually uses the QCD factorization, it sees like kind of a huge deviation, like a big, huge deviation what Bell recently has published, I mean, put in the archive. So then the idea is there are 2 ways. Whenever you see deviation, either go and try to build some model, new physics model. So there is this group of people there. In that sense, WPI models are kind of favorite to explain this puzzle, I would say. But of course, you can see these are 4 quark operators. So there are some huge constants on the direct searches, say, if going to 2 jets and from the LHC. But in another sense, since these are like hadronic decay modes, so basically the theory estimates has to be carefully looked at, and there has been quite some effort going on to compute the missing pieces from the theory side. For example, the missing part of the form factors, and also some kind of scattering effects, which are also evaluated. But in my understanding, we still need more efforts to actually understand the QCD factorization in this mode. So I just try to conclude. So I was trying to show you various puzzles or anomalies in B decays, which are persisting there for say several years. So this RK star, D star, and also muon G -2 in the other sense. And also this is interesting. I didn't talk about VCV puzzle. I think we heard about it yesterday. So the point is, if we try to really see what kind of new physics effects are there, it might be possible that they are correlated or they are not correlated. I try to highlight in terms of the scales which can be involved in these channels. And also it's possible that there can be some parts from the theory side which is missing, or can be some experimental flaws which can actually lead to evaporation of some of the anomalies. But the point is like the flavor physics is not just to deal with these anomalies. These anomalies will come and go, and if we are lucky, we will actually observe or get the hint just like we got for the charm quark. But if we are not, we are in a very crucial time, because LHCb and the Bell, they are running, and they will be running for say, I don't know, 10 more years. So, and they are actually evaluating so many decay modes where we don't even have the predictions from the theory side. So whatever the number they are given, in some cases we don't know even what to compare. So forget about getting any anomaly in those channels. So my point of view, so a lot to understand from the hadronic side. So theory efforts must be put into this topics. So thank you very much for your attention.
Thank you. Questions? Okay, Dipankar.
Okay, Rusa. So my first question is about this B to S transition that you described. So you discussed leptoquarks, right? I think it is related to the previous question that Tuhin asked. So we know that if we, to the standard model, if we add the leptoquarks, then we can explain those anomalies. But I think your point was if we add it forcefully, then the Yukawa couplings that we introduce, those are arbitrary, and you have to fit them retrospectively from the data. And let's say you get them small. So your objective is to basically explain those smallness by embedding the leptoquark model in a Froggatt-Nielsen framework. so that that smallness of the Yukawa coupling gets translated into number of fermion lines that you introduce, right? But I did not see any like quantitative remark on the, let's say, the flavor symmetry breaking scale or this masses. So does this fit give you any idea about those?
Yes, so those masses you can, the fermion masses you can push up to, I don't know, even Planck scale.
No, I know that is in principle I can push, but if I want to fit the B2S data,
Yes.
does that give me any hint about that scale?
Yes, indeed. So it depends on like how you are actually embedding, right?
So you had a model, right?
My model is kind
You
of
you want
low energy. Still it's in the EFT one. I still didn't show you how to actually get those operators with so many fermions in the model, right? So in that sense, it's still not a full model. It's just a framework which is saying how to actually motivate the the EFT operators, the 4 fermion operators from a UV point of view. But for a full model, you of course need the fermions and then you need to compute the scales.
all right, okay. It's basically hiding the smallness of this Yukawa behind.
The SU3 of Q and SU3 of U, and the corresponding Froggatt-Nielsen charges, the U1 that you have chosen.
Yes.
Doesn't it look like it's not commuting back and I mean, it's
so
not,
this
isn't it?
one I have chosen, it is not not obeying the MFP. It is beyond MFP.
So you have to make sense now. So it's a framework, so it needs to make sense. So how does it make sense to have both SU3s as well as your U1, that particular U1 at the same time?
Maybe okay. Where is my slide? Okay. I mean, maybe I didn't get your question properly. So you are saying we can't have the U1 on top of the SU3?
No, we motivate that there is a specific, like the MFB, the way you got that polynomial, YU square, YD square, and things like that.
Yes. So in my case, MFB is not followed. It's the leptoquark is generating extra source of flavor violation. So that was my point, that MFB cannot explain the B anomaly. So we need to go beyond it.
Like the 8 operators which MFB permits you, and then on top of it you put different Froggatt-Nielsen constraint.
No, we added extra source of flavor violation through the leptoquarks, through Froggatt-Nielsen. This is not at all MFB framework.
But then you have a large number of operators, no?
So that's what I showed. Like if we have, I can't show the slides, but if you have the Froggatt-Nielsen embedded in leptoquarks, so then the number of parameters are for one operator, say 20.
Okay, so then I missed it.
Okay, thanks.
Other questions, comments? Okay.
Just a small comment. You showed the HVP thing as measured from the data and the BMW. Okay, so of course, if one assumes the BMW, then the discrepancy in G-2 goes away.
Not goes away.
I mean, it reduces significantly. But on the other hand, if we accept that, the delta alpha, the fine structure constant, that fitting goes for SX, right? Crevelin et al. Have shown that, and some others too, I think, Marciano. And similarly, some other variables also
goes bad.
So probably it's still under discussion.
Somewhere in between. So,
yeah, maybe.
Yeah, thanks.
Okay, if there are no other questions, let us thank the speaker again. So
So I first of all thank the organizers for giving me this opportunity to share some of the work we are doing in our group. Fortunate that is coinciding with when Messi is on the ground, but okay, I cannot do anything about it. But okay, I'm going to talk about some phenomenological studies on composite Higgs models that we have carried out in the last few years. And it would have been appropriate to just go to the results, but please bear with me while I share some very basic slides to introduce my results. So as we have now discussed this several times, that the discovery of the Higgs has updated the standard model particle spectrum in a non-trivial sense, because if you assume that the Higgs is an elementary particle, then unlike the chiral fermions and the gauge bosons, it does not have, of course, any symmetry that can insulate it from the UV. This itself is incongruent. And if you further assume that there is a physical high scale that the standard model couples to, this is disastrous and leads to this hierarchy problem. Now, there is, of course, a several multitude of avenues by which this has been addressed over the last several decades. But one very simple possible way out of this pickle is to assume that the Higgs itself is composite. And therefore, in the UV, it basically dissolves into its constituent particle. And you can imagine that in the UV, there are no fundamental scalars at all. So it is just made up of things which can be symmetry protected. So even if you do not care about this argument of composite Higgs as a solution to the hierarchy problem, now that we have the Higgs and we are truly in what we call the Higgs era, I think it's a legitimate question to ask whether this particle that we have found is in point like a fundamental particle, or does it have some non-trivial shape, and which would mean that we can ascribe some kind of a size to it, some kind of a charge radius, if you may. And associated with such a size, of course, would be a scale, which is the compositeness scale of the of this Higgs scalar. And the idea is that below this compositeness scale, the Higgs lives as a composite object of more fundamental particles. Whereas as it crosses this threshold of the compositeness scale, it basically dissolves into more fundamental constituents. And the assumption is that none of these constituents are scalar. And as long as you can generate this compositeness scale naturally, maybe through something like dimensional transmutation, you have a kind of an handle to address the hierarchy problem. Of course, the most natural thing to do would be to assume that all the dimensionful parameters of your theory is connected to this, quote unquote, natural compositeness scale. So you assume the Higgs mass or any other resonances of this underlying strongly interacting theory to be equal to this compositeness scale. And this was, of course, the original proposal of Technicolor models. However, we knew long before the LHC that this wouldn't work out, because from the oblique electroweak observables which were measured at the Z pole at LEP, we already knew that these new resonances would mess up this oblique parameters. And therefore, you need to create kind of a parametric separation between the scale of compositeness and the Higgs mass. Now, one natural way to drive this is to assume that the Higgs is not only composite, but it's also a kind of a pseudo-Nambu-Goldstone boson of this strongly interacting theory. And then you have a natural hierarchy between the new resonances, the compositeness scale, and the weak scale. That would survive this electroweak observable test from LEP. So, in some sense, this PNGB composite Higgs program can be schematically described in this way, that on one end, you have, of course, the standard model with all the elementary particles except the Higgs, and then you invent this strongly interacting sector that is responsible for confining some preons or technifermions into the Higgs. And then the Higgs is actually identified as a Goldstone mode of some global symmetry G breaking to some subgroup H. So you assume the strong sector is responsible for both of these things, breaking the global symmetry and also confining and producing the composite Higgs. Now, of course, even the one way you can give some mass to this Higgs is to invent a kind of a linear mixing between this composite sector and the standard model sector. And this is what is known as partial compositeness. So the idea is that you assume that the strong sector also has some operators which have the same quantum numbers as the resonances of the standard model. In that case, you can write down some linear mixing between these. And since the standard model does not care about any global symmetries of the strong sector, these linear mixings will explicitly break the global symmetry in the strong sector and give a radiative mass to the composite Higgs. So in some sense, the bare essential properties of this strong sector should be that it should produce the Higgs, it should confine some underlying chiral fermions to form the Higgs. But on top of that, it should also be able to have operators which have same quantum numbers, let's say as the colored quarks in the standard model, or maybe even the gluon. So you need, quote unquote, these top partners and these vector partners. In case you are worried as to how this kind of a theory can be driven in the UV, I have just one slide to try to convince you that this is nothing but QCD, which is just again promoted with to another sector. It's a QCD-like theory where you have to just have some fundamental fermions having some confining gauge theory, and that produces a meson, and you basically identify the Higgs as the pion of this new QCD-like theory. Now, again, coming back to the bottom-up approach to this, basically, if you pare it down, the entire picture would look something like this. You, of course, have the weak scale, and sitting around the weak scale is this composite Higgs, which is, of course, made up of some underlying particles. And then in the TeV scale, you have to have all these new resonances which are required for partial compositeness. And then you have the cutoff. Interestingly, these masses of these resonances are linked with the mass of the Higgs because after all, the mass of the pseudo-Goldstone boson Higgs is generated because of these resonances. Okay, so there's a connection between these two sectors. So if you want to take a pot shot at this picture using the LHC, you have, let's say, 3 prime targets. One is that you can look at the low-lying fruits of these colored resonances, which should show up in this theory around the TeV scale. These are the so-called top partners or the gluon partners, and one can do a direct search for them. The other possibility is that, of course, this Higgs is non-linearly realized because it's a pseudo-Nambu-Goldstone boson. So following the CCWZ construction, it is non-linearly realized, and therefore you would expect, even at the weak scale, that there will be a correlated deviation of the Higgs coupling from the standard model prediction, which would be parameterized by the ratio of the weak scale and the the compositeness scale. However, in my opinion, the best way to look for compositeness of a Higgs is to search for it in the off-shell mode, where you can actually probe the momentum dependence of the Higgs. After all, if the Higgs is composite, then its coupling to other fundamental particles would be momentum dependence, where the scaling is more than the simple logarithmic scaling. And one can probe, if one can probe this aggressive momentum dependence of the couplings, that would be a telltale sign that the Higgs is composite. So this is like doing deep inelastic collision for the Higgs. So I would like to very briefly go through some work that we have done in these 3 directions and very quickly flash some results. So in terms of the searches for strong resonances, this is of course a very large literature on this. The only thing that we try to point out is that if these resonances arise from the strong sector, they would have, because they are members of strong sector, presumably having strong decays within that strong sector, they will have very large widths, and they might start violating the narrow width approximation. And one needs to be careful into taking into account this finite width effect of these broad resonances. So, for example, in this plot, as you can see, this is just some, translation of some collider bounds on the parameter space of some top partner and its decay width to mass ratio. The important thing here is that the solid lines that you can see are the ones where we take the full 1 pi corrected propagators for these top partners, and the dashed lines are the ones which are using the narrow width approximation. And as you can see, when the width to mass ratio is small, these kind of more or less agree. But if you go to crazy high decay widths of the order of 40 or 50% of its mass, you see more than 20-25% deviation in the limits that you would translate using a narrow width approximation with actually using a trying to at least capture the leading effect of the broadness of these resonances. Okay, so we have over a period of time, together with Deeptimoy and Santosh and many people, we have worked through many of these, trying to translate them using the full 1 pi propagators. And I don't want to go through each of these slides. The basic takeaway message is just simply this, that at present, the limits on the top partners is, of course, expectedly around 1 to 1.5 TeV. And the limit on the gluon partner is around 2 and 2.5 TeV. But in the what we learned from this exercise is that unless we take the full 1 pi corrected propagator, we make an error of around 20% in translating these limits, and for whatever it is worth. But this hunting for exotic resonances is probably not the best way to search for composite Higgs, simply because, of course, you have this handle that you can keep pushing this top partner masses upwards, staying in terms of fine tuning. And not only that, there is this classic inverse problem that even if you see these top partners, you never know, what it means, where it came from. It can be from a plethora of models. So the nearly, yeah, well, okay. Okay, with that plot, we went up to 60%. Yeah, no, I agree with you. I agree with you that this is just captures the essence of the broadness, but probably as you keep going upwards, you have to be more correct in including more and more things into it. So that's why maybe, I don't know, somewhere it will start failing again. Okay, so then moving on to the second very quickly, looking for the correlated deviations in the Higgs coupling that should show up just because the Higgs is non-linearly realized. You can look into the Higgs data. We have now a lot of Higgs data from the run 1 and run 2, and one can check whether you can identify some kind of, because if it is non-linearly realized, you not only expect a deviation of the Higgs coupling, but there's a correlation of how these Higgs would deviate depending on various things like the choice of the coset in the strong sector, of which you are assuming the Higgs is a PNGB off, depending on where you embed your fermions. But modulo these things, you would, once you fix these model parameters, you will have a well-defined set of Higgs couplings deviated from the standard model, parameterized by this quantity, which is essentially the square of the ratio of the weak scale and this strong scale. And we did kind of a global fit for the simplest such composite Higgs model, which is known as the minimal composite Higgs model. And the takeaway from this exercise is, again, these Higgs data already pushes these models to about a percentage level fine tuning, which is similar to the status of, let's say, the SUSY models. Okay. And again, just to emphasize that even if we see such a correlated, deviation, maybe in the the updated runs at LHC or maybe at a future Higgs factory, it would still not be a smoking gun signal of compositeness of the Higgs, because all that we can say is that the Higgs has a deviation which is consistent with a nonlinearly realized model, and probably nothing beyond this. So finally, let me come to another possibility where you can try to look for the momentum dependence of these Higgs and translate them as a indication for the Higgs compositeness. So if you look at this cartoon, what we have over here is that along y-axis, assume that there is some coupling, and along x-axis, it is, let's say, the center of mass energy. So the standard model coupling, okay, this is in the window of present and future colliders. The standard model couplings would be basically, remaining state. It has very soft logarithmic dependence on the momentum due to RG, but other than that, it would be a, it will scale, in a very, very slowly. Whereas now, if you consider the nonlinear realization, all that it will do is that it will create a shift in these couplings. Each coupling will get shifted, but as long as it is still elementary, it would again, while there will be a shift, it would still scale logarithmically with the scale. So so if your Higgs is truly composite and your compositeness scale is in the TeV scale, what you should be able to see is a more aggressive momentum dependence of its coupling, because here the couplings are basically upgraded to be structure functions which have power law dependence on momentum. And if you can see such kind of an scaling of the couplings, that would be in some sense a direct hint of the compositeness of the Higgs boson. So we wanted to do a proof of principle study of whether what can be done in the context of the LHC. So we looked at this HVV coupling. Of course, in the elementary, in the standard model case, it's the coefficient in front of this operator is just a number. And if you think that the Higgs is now a composite object, you have to upgrade this to some kind of a structure function, which, given, energy momentum conservation and in this vertex can depend on two of the momentums in these lines. Okay. Yeah. Yes. No. So just bear with me. I agree with you. So if you put a momentum dependent, first of all, if you put a momentum dependent coupling and derivative coupling, that means it's not the standard model anymore, right? That's already yes. Okay. And so that would already start capturing. So this effective field theory is called the strongly interacting linear Higgs kind of a effective field theory, where you are starting to capture the impact of these momentum dependence in some sense. Yes, but then you have to see how it scales with the off-shellness of the Higgs, and that would be an indication of whether that is included there. So the problem here, of course, is to model how to write down this structure function, because that is non-perturbative physics and it's very difficult to do so. So what we ended up doing is trying to write down what we can using the large N results. So including the 2-point and 3-point functions from the large N, we try to model the structure functions in this form. Assuming that these coefficients are all, these numerators are all kind of constants. And these masses that show up in this, structure functions, of course, are some parameters of the underlying theory, which is confining the Higgs, but you can, in some sense, identify them with the resonances in this large N dynamics. So these are like, masses or resonances, which are identified with the resonances that build the Higgs up. So using this kind of a very simple-minded parameterization, we try to look at this channel is associated production of Higgs with a Z, where the Higgs decays to 2 bottom and the Z decays to 2 leptons. And what you see, and we try to look at a bunch of different, observables and check what can be the impact of this kind of a momentum dependent coupling. For a starter, if you just plot the cross section as a function of the center of momentum energy, you see the red line is of course, the standard model prediction, which has to fall off with root of S to preserve unitarity. And what you see over here are these two, this, I don't know, pink and blue lines, which are the kind of variation that you see if you include this kind of a structure functions modeled with the leading large N results for the structure functions. And this dashed line is the line that you are suggesting, which comes from the strongly interacting linear Higgs, which takes the leading derivative couplings. So this is what you would get from that kind of a scenario. Of course, this is an effective theory. So while the Silch is a very good mimicker of composite Higgs at low energy, it will of course violate unitarity at some scale where the effective field theory fails. A good aspect of using this kind of a structure functions are that they will actually preserve unitarity in the UV. And if you want to concentrate on, let's say, the tails of various distributions, probably this is a more reliable way of modeling them. So using this kind of a framework, we tried to look at a bunch of kinematic distributions, differential distributions of various kinematic parameters, and try to check how it would deviate from the standard model prediction and what are the possibilities to search for them at the high luminosity run of the LHC. So in each of this plot, the red lines or histograms are the standard model prediction, and the pink and the blue is what you get from a composite Higgs-like scenario. And the two lines are assumed, the difference between the two lines is basically we have assumed a broad decay width of these exotic resonances in the propagator, in the structure functions. And in the other case, we have assumed that the decay width is small, around 10% and maybe 40%. So this is why you get these two blue and pink line. So as you can see, for some parameters like the invariant mass of the final state particles or the transverse momentum of the final state leptons, it seems that it's promising and it shows a kind of discrimination. Of course, this is dependent on where your compositeness mass is, what is your compositeness scale, but you can at least hope to see something in this scale. Unfortunately, of course, the present runs for obvious reasons are more focused at the Higgs peak, because that is where you want to look at in this channel. But if this kind of analysis focusing on the tail can be done, we can probably learn a little bit more and constrain the composite, at least if not anything, constrain the compositeness of the Higgs. In this process, yeah. This is the process. Okay. Yes, of course. Well, so if you see here, the way we have modeled this at the level of 3-point functions, we have two resonant masses, and we also assume that they have some kind of a decay width. So we have three independent parameters, the two masses and the decay width, but we have a constraint that this at the low energy should give you the right, the standard model gauge coupling. So essentially it's a two parameter, like two free parameter scenario. Yeah, so I guess this is all that I wanted to say, that, that possibly this study for off-shell Higgs is a way forward for these kind of studies. And we are now trying to also look at what happens if the Higgs is in a loop, which has a momentum dependence and has some consequence.
Questions? Okay, there seems to be no questions asked. So let us thank the speaker again. That's the end of the session. I think we are too early for coffee.